Hello there, and welcome to the Sleep with Science channel. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps the channel to reach more curious minds like yours. Now let's begin. Tonight, we are not going to explain the universe. We are going to wander into it, slowly, the way starlight wanders across 100,000 years just to reach your eye. Somewhere above you, right now, beyond the ceiling, beyond the clouds, beyond the last thin edge of our atmosphere, there is a darkness so old that it remembers a time before time had a name. And inside that darkness, hidden in plain sight, are questions that have quietly outlived every civilization that has ever asked them. What is actually inside a black hole? Why does the universe seem to be expanding faster with every passing year, as though something unseen is pressing its hand against the fabric of space and pushing? Why do galaxies spin as if unseen weight were holding them together, weight we cannot see, cannot touch, cannot photograph, and yet weight that outnumbers all the stars and planets and moons combined by nearly 6 to 1? What happened in the first fraction of a second after everything began? And is there truly an edge to it all, a final shoreline where space simply stops? Or does it curve back gently upon itself, so that if you traveled far enough in one direction, you would eventually return to where you started, only many billions of years older? You do not need to answer any of this tonight. You do not need to hold on to anything at all. Let your shoulders soften into whatever is beneath you. Let your jaw unclench. Let your breath slow, in through the nose, and out, long and unhurried, like a tide retreating from a shoreline no one has ever mapped. Because these mysteries have waited this long already. They can wait a little longer while you rest. Let's begin where all of it begins, with scale, because before the mind can hold a mystery, it must first hold its size. Picture the Earth, small and blue and quiet, spinning at nearly 1,000 miles an hour, though you feel none of it. Now picture our Sun, so large that more than 1 million Earths could fit inside it, and yet our Sun is a modest, ordinary star, one of perhaps 200 billion stars in the Milky Way alone. Now step further back. The Milky Way itself is only one galaxy among an estimated 2 trillion others scattered through the visible universe, each one holding its own 100 billion suns, each sun perhaps holding its own quiet planets, spinning in the dark, unnoticed, unnamed. And even that staggering number, 2 trillion galaxies, is only what we can see. Light from the very edge of the observable universe has been traveling toward us for over 13 billion years, which means when you look far enough into the night sky, you are not looking outward so much as you are looking backward, into the deep and folded past. Everything above you tonight is, in some sense, a memory. Let that settle over you like a slow, heavy blanket. You are lying beneath a ceiling of ancient light, some of it older than the rock beneath your house, older than the rivers, older than any word ever spoken by anyone. And somewhere in that vast and silent field of memory are the mysteries we will spend our night drifting through together, unhurried, one gentle layer at a time. Not solved tonight. Not rushed tonight. Only approached, the way you might approach the edge of a dark lake, barefoot, unsure of the bottom, content simply to stand at the water's edge and listen to it breathe. Consider, for a moment, the simple journey of light. It moves at 186,000 miles every second, faster than anything else we have ever measured, and still, it takes light from our own sun a little over 8 minutes just to reach your skin. 8 minutes for something moving at the very speed limit of the universe. Now imagine light leaving a star so distant that by the time it reaches your eyes tonight, the star itself may have already changed, may have already grown old, may have already died in a brilliant and silent collapse thousands of years before you were born. You are, in this very moment, looking at ghosts. Beautiful, patient ghosts of light. And if you could somehow drift out there yourself, past the moon, past the orbit of Mars, out into the vast and silent gaps between worlds, you would find something strange waiting for you. True silence. Not the silence of a quiet room, but the complete absence of sound itself, because space is nearly a perfect vacuum, and sound has nothing to travel through, no air to carry it, no medium to hum along. Out there, the loudest explosion in the universe would arrive at your ears as absolute, total stillness. And it is inside that vast stillness, that endless silent dark, where the strangest questions in science are quietly waiting for us, folded into the space between what we know and what we cannot yet explain. And of all the folds hidden inside that endless dark, none is quite as strange, or quite as strangely beautiful, as the black hole. Say the words to yourself, slowly, and notice how they feel almost impossible on the tongue. A hole. In space itself. Not a hole in the ground, not a hole in a wall, but a place where space and time fold so completely inward that they simply stop behaving the way they do anywhere else in the universe. You do not need to understand this fully tonight. You only need to drift alongside it, the way a leaf drifts along the surface of a slow, dark river, never touching the bottom, never needing to, carried gently by a current far older than itself. Just let the shape of the idea move through you. Picture a star, vast and burning, many times larger than our own sun. For millions of years it holds itself together through a kind of perfect balance, a tug of war between its own outward light and its own inward gravity. And then, one day, quietly, the fuel runs out. And gravity, patient gravity, finally wins. The star begins to collapse in on itself, faster and faster, crushing inward with a force so complete that matter itself is no longer matter as we know it. It collapses past the size of a planet, past the size of a mountain, past the size of a single city block, down and down, smaller and smaller, until what remains is not a thing you could ever touch, but a point. A single point, so dense, so impossibly compressed, that gravity around it becomes strong enough to bend light itself. This is the boundary scientists call the event horizon, and it is one of the strangest borders that has ever been drawn. Not a wall, not a surface, nothing you could ever press your hand against. Just an invisible threshold hanging quietly in the dark, where the ordinary rules of coming and going gently, permanently, dissolve. Cross it, and there is no crossing back. Not because of speed, not because of distance, but because beyond that line, every path forward, every possible direction you could ever travel, leads only inward. Some physicists describe it gently, almost like a lullaby themselves, saying that beyond the horizon, the future itself points toward the center. There is no outward left to travel. Let that settle over you slowly. A place where forward and down become the very same word. And here is where the true mystery begins, the one that has kept some of the most brilliant minds awake at night, turning the problem over and over like a smooth stone in the palm of a hand. What is actually at the center? Our equations, the same equations that predicted black holes decades before we ever photographed one, tell us that all of that collapsed matter should shrink down to a single dimensionless point, a singularity, where density becomes infinite and the rules of physics simply stop giving us answers. Not wrong answers. No answers at all. It is the place where our best understanding of gravity, built by Einstein over a century ago, quietly raises its hands and goes silent. Somewhere, at the heart of every black hole, from the small ones born from dying stars to the almost incomprehensibly massive ones sleeping at the centers of galaxies, there may be a point where the laws that govern the falling of an apple, the swinging of a pendulum, the orbit of a moon, simply cease to apply. And no telescope we have ever built, no telescope we may ever build, could look inside and see it directly, because light itself, the very thing our eyes and our instruments depend upon, cannot escape to carry the image back to us. We are left forever on the outside, watching only the edges, only the shadow, only the gentle, curved bending of starlight as it slips past the boundary and vanishes. In April of 2019, for the first time in human history, We did manage to capture an image of one of these shadows, a faint, glowing ring of light bent around darkness, over 50 million light-years away, in a galaxy called Messier 87. Let that number rest in your mind for a moment. 50 million light-years. The light captured in that photograph left its source 50 million years before the first humans ever stood upright on this earth. It traveled quietly, patiently, through the endless black, long before there were eyes anywhere to receive it, and it kept traveling anyway, as though it somehow knew that, eventually, someone would be watching. And at the center of that glowing ring, inside that perfect circle of bent and struggling light, was nothing. Or rather, nothing that we could see. A darkness so complete that our instruments simply recorded an absence, a silence shaped like a circle, sitting at the very heart of a galaxy, holding the orbits of countless stars in its invisible grip. We know it is there. We can measure its pull. We can watch stars swing wildly around it, obeying its command. And yet the thing itself, the true center, remains hidden from us, wrapped inside its own boundary, keeping its deepest secret exactly where it has always kept it, just beyond the reach of anything we have ever built, or anything we may ever build to look. Let your breathing follow the shape of that thought. In and out. Slow, unhurried, patient, the way light itself bends slowly around the soft curve of that dark and silent ring. There is no need to hold onto the mystery tightly. Let it rest beside you instead, like a stone gathered from a riverbank, smooth and quiet, carried simply because it was beautiful, not because it needed to be understood. Now imagine, just for a moment, that you yourself could drift toward the edge of one of these strange places. Not to fall in, only to watch, from a safe and impossible distance, the way time itself would begin to bend around you. This is one of the gentlest and strangest truths in all of physics. Time is not the same everywhere. It does not tick at the same steady pace for everyone, in every place, under every amount of gravity. Near a black hole, gravity grows so overwhelming that time itself begins to slow down, the closer you drift toward that invisible boundary. If you could somehow hover just above the event horizon, watching a friend far above you, safely aboard a distant ship, you would see their clock ticking faster and faster, their whole life rushing past in what felt to you like only a few quiet hours. And if your friend watched you instead, they would see the opposite. Your movements would slow. Your clock would stretch. Your final approach toward that boundary would appear, to them, to take almost forever, your image growing dimmer and dimmer, redder and redder, fading softly into the dark, as though the universe itself were gently, slowly, closing a curtain. You would never appear, to them, to actually cross the line. You would simply fade, suspended forever at the very edge of their sight, even as you, in your own experience, crossed it in an instant. Two people, two truths, both real, both entirely true, at exactly the same time, without contradiction. This is not a trick of the eyes, or an illusion, or a limitation of our instruments. It is the honest, physical nature of time itself, flexible, relative, bending under the weight of gravity the way a heavy stone bends a soft sheet of fabric stretched taut beneath it. Let that settle over you slowly. Time is not a river flowing at one steady pace for the whole universe. It is something closer to breath, closer to tide, moving differently depending on where you stand and how deeply gravity is holding you. And there is another mystery here too, quieter still, one that even now divides some of the most careful minds in physics. What happens to everything that falls in? Not just light, not just matter, but information itself, the complete and total description of everything a thing once was. Every particle that has ever crossed that boundary carried with it a kind of story, a precise arrangement, a fingerprint entirely its own. And the deepest laws of physics, the ones that have held steady through every experiment we have ever run, insist that this information can never truly be destroyed. It can be scrambled. It can be hidden. It can be rearranged beyond any hope of reading. But erased completely, entirely, forever, gone. That, physics says, should not be possible. And yet black holes, patient and dark, seem to slowly evaporate over unimaginable stretches of time, releasing a faint whisper of radiation first predicted by the physicist Stephen Hawking, a slow and gentle leaking of energy at the very edge of the horizon. And if a black hole evaporates completely, fading at last into nothing, then what becomes of everything, and everyone, and every story that ever fell inside it? Does the information somehow escape, hidden quietly within that faint and glowing radiation? Does it remain, forever locked away, in some deeper reality we cannot yet see? Or is there, somewhere in our understanding of the universe, a rule so fundamental that we have not yet discovered it is even breakable? This gentle puzzle has a quiet name, almost as soft and unassuming as its nature. Scientists call it the information paradox, and it remains, to this day, one of the most unresolved tensions between two of our greatest theories, the smooth, curved, gravitational world described by Einstein, and the strange, probabilistic, flickering world of quantum mechanics, where particles exist as possibilities until the moment they are observed. Somewhere, at the heart of every black hole, these two descriptions of reality are forced to meet, and so far, they have never fully agreed on what happens next. Let this thought drift now, unresolved and unhurried, the way a single small ember drifts slowly upward from a dying fire, glowing faintly, rising slowly, never quite reaching the dark ceiling of the night sky before it fades from view. You do not need an answer tonight. You only need to simply notice the shape of the wondering itself, soft and open, like a hand resting gently, palm upward, beneath a sky it may never fully hold. And somewhere far above that sky, past even the reach of gravity's strangest bending, another kind of mystery has been quietly waiting all along, one that concerns not the edges of a single collapsed star, but the very fabric of space and time themselves. Not a mystery hiding within one dying star, but a mystery woven through the entire endless dark, present in every direction you could ever look, present even here, quietly, in the empty air just above your resting body. Let your eyes stay closed, heavy and still. There is nothing to search for, nothing to find, only a soft and steady noticing, the kind that happens all on its own when the mind is finally, gently, allowed to fully rest. Breathe in, slow and full, and breathe out, slower still. Let your body sink one small degree deeper into whatever is holding you. Good. Now let's drift, together, toward the next quiet mystery, the one written not into a single collapsed star, but into every galaxy that has ever spun, silently, through the dark. Picture a galaxy. Not ours, not yet, just any galaxy, turning slowly in the black, a vast pinwheel of light containing hundreds of billions of stars, all held together, all kept from flying apart, by gravity alone. Now, gravity is a simple thing, or at least it seems simple. The more mass something has, the more strongly it pulls. And so, decades ago, astronomers assumed that a galaxy's stars would behave the way planets behave around our sun. The ones near the busy, crowded center, where most of the visible mass sits glowing and bright, should move quickly, caught in a tight and hurried orbit. And the ones drifting near the faint, quiet outer edges, far from that concentrated light, should move slowly, gently, barely tugged at all by such distant gravity. But when astronomers actually measured it, in galaxy after galaxy, decade after decade, they found something that should not have been possible. The stars at the outer edges were not moving slowly at all. They were moving nearly as fast as the stars near the center, spinning around their galaxy's core at speeds that should have flung them off entirely, sending them tumbling out into the empty dark, the way a stone flies loose from a sling swung too quickly. And yet, they did not fly apart. Something, some vast and unseen presence, was holding them in place, holding entire galaxies together with a gravitational grip far stronger than all of their visible stars, gas, and dust could ever provide on their own. Let that settle over you slowly, gently, the way a held breath finally, quietly, releases itself into the dark. Something is out there, wrapped gently around every galaxy we have ever studied, invisible to every telescope we have ever built, present in radio waves, in visible light, in the faintest whispers of infrared, and yet somehow, impossibly, never once directly seen. We have given this unseen presence a name, though the name itself admits how little we understand it. We call it dark matter. Not because we know it is dark the way a shadow is dark, but because it does not interact with light. It does not glow. It does not block starlight the way a planet would, casting a small and measurable shadow. It simply is not visible. Not now. Not with anything we currently possess. And the strangeness does not end there. When scientists carefully add up everything this unseen material must weigh, based purely on its gravitational pull, based on how tightly it must be holding these galaxies together, they arrive at an almost unbelievable number. Dark matter appears to outweigh all of the visible matter in the universe, every star, every planet, every moon, every wisp of glowing gas, combined, by more than 5 to 1. Which means that everything you have ever seen, every photograph from every telescope, every star you have ever wished upon on a clear and quiet night, represents only a small, thin fraction of everything that actually exists. We are, in the truest sense, surrounded by far more of the universe than we have ever laid eyes on. Some scientists believe dark matter is made of an entirely new kind of particle, one that barely interacts with anything at all, drifting silently through stars, through planets, through the very room you are resting in right now, passing through your body by the trillions, every single second, leaving no trace, no warmth, no sound, no evidence of its passing. Others wonder if our understanding of gravity itself might simply be incomplete, if the equations we trust so deeply might need a gentle correction we have not yet discovered. Deep underground, in laboratories built inside old mines and beneath ancient mountains, shielded from the noise and interference of the surface world, scientists sit quietly in the dark, waiting, watching sensitive detectors for the faintest possible sign, a single, gentle collision between a dark matter particle and an ordinary atom, a whisper so faint it might come only once in a great while, if it comes at all. And so dark matter drifts quietly through everything that exists, patient and utterly invisible, holding entire galaxies in its unseen embrace, present in this very room, in this very breath, in the space between your fingers as they rest, unmoving, at your sides. It asks for nothing. It offers no light. And yet without it, every galaxy in the universe, including our own quiet spiral home, would have unraveled long, long ago, its scattered stars slowly unraveling outward into an emptier, colder, darker. An emptier, colder, darker place, where no spiral arms would curl in their slow, patient turning, where no nurseries of stars would ever have had the gravity to gather themselves out of the thin, drifting gas. Dark matter is the silence that holds the music together. It is the unseen hand cupped gently beneath the flame, keeping it from guttering out into the dark. And here, in this quiet room, as your breathing slows and your body settles deeper into stillness, let your mind drift outward, past the walls, past the sky, past the moon hanging pale and patient in its old familiar orbit, out to where the galaxies themselves begin to reveal a stranger secret still. Because dark matter, mysterious as it is not the universe's only invisible hand. There is something else out there. Something larger. Something stranger. Something that does not gather and cluster and pull things together, but instead pushes everything apart. Astronomers call it dark energy, though the name, like so many names given to things we do not yet understand, is really just a placeholder for a shape in the mathematics, a gap in the equations where something unseen must be sitting, quietly doing its work. In the late 1990s, two teams of scientists, working independently, watching the light of distant exploding stars called supernovae, found something that should not have been possible. They expected to find the universe's expansion slowing down, gently easing its foot off the pedal, the same way a ball thrown into the air slows as gravity pulls it back. Instead, they found the opposite. The universe was not slowing. It was speeding up. Galaxies were rushing away from one another faster and faster, as though someone, somewhere, was pressing down harder and harder on some vast, invisible accelerator. Let that settle into you for a moment, the way warmth settles into a body sinking into a soft bed. The universe is not simply expanding, the way a balloon expands when filled with breath. It is expanding while accelerating, stretching space itself faster with each passing year, carrying galaxies away from each other at a rate that grows and grows, without any sign of slowing. And whatever is causing this, whatever invisible pressure is pushing against the very fabric of space, makes up, by current estimates, nearly 70% of all the energy and matter in the entire universe. Dark energy. The largest single component of everything that exists, and we do not know, not truly, what it is. Picture space itself, not as an empty stage on which stars and galaxies simply sit, but as something with its own quiet, restless nature, something that can stretch, that can bend, that can carry galaxies along with it like leaves resting on the surface of a softly flowing river. Einstein once introduced a term into his equations, a small constant he called the cosmological constant, meant to hold the universe still, to keep it from collapsing under its own gravity, back when scientists believed the universe was static, unchanging, eternal in its stillness. He later called it his greatest blunder, removed it, set it aside. But the universe, it turns out, had its own ideas. When the acceleration was discovered decades later, that same constant, or something remarkably like it, needed to be brought back, not to hold the universe still, but to explain why it would not stop stretching. Some scientists believe dark energy is simply a property of space itself, an energy woven into the vacuum, present even in regions utterly empty of stars, planets, gas, or dust, a hum beneath the silence, a low and constant pressure built into the architecture of nothingness. Others wonder if it might be something far stranger, a field that changes over time, growing or weakening as the universe ages, a slow tide with a rhythm we have not yet learned to read. And a smaller number of researchers ask an even deeper question, whether our understanding of gravity itself, so carefully built by Newton and refined by Einstein, might simply be incomplete on the largest of cosmic scales, whether the acceleration we see is not a new form of energy at all, but a signal that the old rules bend and change when stretched across billions of light years. Whatever the true answer turns out to be, the implications settle over the mind slowly, the way night settles over a wide open field. If dark energy continues its quiet work, unchanged and undiminished, then the universe we live in has already chosen its own ending, immeasurably far from now, but chosen all the same. The galaxies that fill our night sky, the countless soft smudges of light captured by our deepest telescopes, will drift farther and farther apart, their light stretching, dimming, fading beyond the reach of any future eye. A slow, gentle scattering. Not a violent ending, not a final explosion, but something quieter, something almost tender in its inevitability, a long fading of light into darkness, of togetherness into isolation, of a universe once dense with galaxies slowly emptying itself out into a cold and silent solitude. And yet, this ending, if it comes at all, lies so far in the future that it holds no urgency, no fear, only a strange and distant kind of peace. The way knowing a candle will eventually burn down does nothing to dim its warmth in this very moment, in this very room, where you now lie safe and warm, drifting somewhere between waking and sleep, while overhead, unseen and unheard, the galaxies continue their slow, accelerating drift into darkness, into a solitude so vast it defies the mind's ability to hold it, each galaxy becoming an island unto itself, adrift in a black and silent sea, further from every other island with each passing eon, until, at last, from within any one of those scattered galaxies, all the others would fade entirely from view, swallowed not by distance alone but by the accelerating stretch of space itself, carrying them beyond the reach of light. A future so quiet, so empty, that it can only be imagined the way one imagines falling asleep, a slow surrender, a gentle dimming, not fought against, simply allowed. But let your mind rest now from that far horizon, and turn instead towards something closer, something stranger still, something that has haunted human imagination since long before telescopes ever existed to confirm it. Somewhere in the darkness above you, hidden among the countless points of light, there are places where light itself cannot escape. Not dimmed, not slowed, not scattered. Simply gone, swallowed whole, extinguished before it can even begin its journey outward. We call them black holes, though the name, like dark matter, like dark energy, is only a word reaching for something the mind can barely hold. Picture a star, vast beyond imagining, many times larger than our sun, spending millions of years quietly burning through its fuel, holding itself up against the crushing pull of its own gravity through the sheer outward pressure of nuclear fire at its core. And then, one day, the fuel runs out. The fire dims. And with nothing left to push outward, gravity, patient gravity, which had been held at bay for so long, finally wins. The star collapses inward, not gently, but in an instant of unimaginable violence, matter falling in on itself so completely, so absolutely, that it passes beyond any known state, compressed past the point where atoms can remain atoms, past the point where even the particles within atoms can remain themselves, collapsing toward a single point of infinite density that our equations call a singularity, a place where the very language of physics breaks down, where our finest and most trusted theories simply stop making sense. Around that singularity forms something stranger still, an invisible boundary in space called the event horizon, a line with no wall, no substance, no visible marker of any kind, and yet a line that cannot be uncrossed. Approach it from the outside, and you would notice nothing unusual as you drew near, no shimmer, no resistance, only the slow, silent tightening of gravity's grip. But cross that boundary, and every path forward, every possible direction you could choose to move, would lead only inward, toward the center, the way every moment of your life leads only forward through time. Inside the event horizon, space and time seem to fold into one another, trading places in the equations, until moving toward the singularity becomes not a choice of direction but an inevitability, as fixed and unavoidable as tomorrow following today. Nothing, not light, not matter, not even information itself, can climb back out once it has fallen past that edge. This is why black holes appear black, not because they are made of some strange dark substance, but because they have carved out a piece of the universe from which no light can ever return to tell us what lies within. We do not see black holes directly. We infer them, the way one infers a whirlpool by watching how the water around it moves, the way one senses a held breath by watching the stillness of a chest. We watch stars orbiting something unseen, whipping around an empty point in space at speeds that only overwhelming gravity could explain. We watch gas and dust spiraling inward, heating to unimaginable temperatures as it falls, glowing brightly in X-rays just before it vanishes entirely from view. And in 2019, humanity captured something remarkable, an image, faint and orange and softly glowing, of the shadow cast by a black hole's event horizon, silhouetted against the swirling light of matter falling in around it, a photograph of the edge of nothing. At the center of nearly every galaxy, including our own, astronomers believe a supermassive black hole quietly resides, millions or even billions of times the mass of our Sun, sitting in patient stillness at the heart of its galactic home, not consuming everything around it in some violent frenzy, as imagination might suggest, but for the most part simply existing there, calm, dark, and largely undisturbed, its gravity gently shaping the slow orbits of the stars around it the way a stone, dropped into still water, shapes the ripples that spread outward from it. Our own galaxy, the Milky Way, cradles one such giant at its center, a black hole named Sagittarius A star, its mass equivalent to roughly 4 million suns, compressed into a region smaller than the orbit of Mercury, sitting there now, in this very moment, 26,000 light-years away, invisible, immense, and utterly silent, as it has been for longer than our species has walked upright beneath the stars, as it will remain long after we are gone, a quiet anchor at the center of everything we call home. Let yourself imagine, for a moment, what it might mean to fall toward such a place, not with fear, but with the calm curiosity of someone watching a dream unfold from a safe distance. Physicists describe a strange and gentle horror in the mathematics of falling into a black hole, something they call spaghettification, a word almost too playful for what it describes. As you fell feet first, the gravity pulling on your feet would grow so much stronger than the gravity pulling on your head that your body would begin to stretch, slowly at first, then faster, drawn out long and thin, the way taffy stretches between two slowly parting hands. For a black hole the size of the one at our galaxy's heart, this stretching would happen gradually enough that you might fall for a long while before it became noticeable at all, drifting inward in silence, watching the stars behind you smear and brighten, watching the universe outside grow strange, until, at last, you crossed the horizon and vanished from the sight of anyone who might have been watching forever. But here the mind runs into one of the strangest riddles hidden inside modern physics, a puzzle that has quietly troubled some of the most brilliant thinkers of the last century, and troubles them still. What happens, in the end, to everything that falls in? Not just the matter itself, the atoms and particles, but the information, the complete and total description of everything that object once was, every detail of its structure, every arrangement of its particles, all the quiet data of its existence. Physics, in its deepest foundations, holds a principle that many believe to be unbreakable, that information can never truly be destroyed, that the universe, however chaotic it may seem on its surface, keeps a perfect and unerring account of everything within it, the way a vast and silent ledger records every transaction, never losing a single page. And yet black holes seem, at first glance, to violate that principle entirely. Stephen Hawking, in the 1970s, discovered something remarkable and unsettling, that black holes are not perfectly black after all, that on the deepest quantum level, at the very edge of the event horizon, pairs of particles occasionally flicker into existence, borrowed briefly from the vacuum of space itself, and sometimes, only sometimes, one particle of that pair falls inward while the other escapes outward, carrying a small amount of energy away from the black hole. Over immense stretches of time, longer than the current age of the universe by almost incomprehensible margins, this slow leak of what we now call Hawking radiation would cause even the largest black holes to lose mass, to shrink ever so slowly, and eventually, unimaginably far in the future, to evaporate entirely, fading out of existence not with violence, but with a final, quiet whisper of radiation scattering into the dark. But if a black hole can fully evaporate, fully disappear, then what becomes of everything it once swallowed? What becomes of the information describing every star, every planet, every fragment of matter it consumed across its long lifetime? Does it simply vanish along with the black hole itself, erased from the universe's ledger entirely, a page torn out and burned? Or is it somehow preserved, encoded subtly within the pattern of that escaping radiation, smuggled out particle by particle, so quietly and so thoroughly scrambled that from the outside it would look like nothing more than random noise, static without meaning, and yet, in principle, if studied closely enough, fully reconstructible, like a shredded letter that could, given enough patience, be pieced back together? This question, known simply as the black hole information paradox, has occupied some of the finest minds in physics for decades, and remains, even now, only partly resolved, a place where our understanding of gravity and our understanding of the quantum world, two of the most successful theories ever developed by human beings, seem to quietly contradict one another. Some theorists believe the answer lies in something called black hole complementarity, the strange idea that from the perspective of someone falling in, nothing unusual would seem to happen at the horizon at all, while from the perspective of someone watching from a safe distance, that same falling object would appear to burn up instantly at the edge, its information smeared thinly across the horizon like heat across a stovetop. Both descriptions somehow equally true, depending only on where the observer stands, a paradox resolved not by choosing one answer over the other, but by accepting that reality itself may simply look different depending on who is watching and from where. It is a strange kind of comfort, in its own way, the idea that the universe does not demand a single, rigid answer to every question, that some truths may be allowed to depend on perspective without breaking apart into contradiction, the way a single piece of music can sound entirely different depending on whether you are the one playing it or the one simply listening, half asleep in a darkened room. Let your thoughts drift now, gently, away from the crushing gravity of black holes, towards something quieter, something that surrounds you at every moment without your ever noticing it, the fabric of space and time itself. We speak of space and time so casually in ordinary life, as though they were simply the empty stage upon which everything else takes place, an unchanging backdrop against which the true drama of existence unfolds. But Einstein, in the early years of the last century, revealed something far stranger, something that still resists full comprehension even after more than 100 years of careful study. Space and time, he showed, are not separate, are not fixed, are not merely a stage at all. They are woven together into a single fabric, spacetime, and that fabric can bend, can stretch, can ripple, can curve beneath the weight of mass and energy the way a heavy stone placed on a taut sheet causes the sheet to sink and curve around it. This is what gravity truly is, not an invisible force reaching out across empty space to pull one object toward another, as Newton once imagined, but the simple and elegant consequence of mass curving the very geometry through which all things move. A planet orbits a star not because some string of force reaches out and holds it in its path, but because the star's mass curves the space around it, and the planet, moving in what feels to it like a perfectly straight line, is simply following the natural curve of that bent and folded geometry, the way a marble rolling across a warped table will trace a curved path not because it is being pulled sideways, but because the surface beneath it is no longer flat. Gravity, in this light, becomes something closer to geometry than to force, something written into the architecture of existence itself. And if space and time can bend, then time itself, the steady ticking we so rarely question, the quiet rhythm beneath every breath you take as you rest here now, is not so steady after all. Time moves differently depending on where you stand, and how fast you move, and how strong the gravity around you happens to be. Clocks placed near a massive object, deep within a strong gravitational field, run more slowly than clocks placed farther away, in a weaker field. This is not some abstract mathematical curiosity confined to the far reaches of the universe. It is measurable, provable, present even here, even now, in the quiet room where you lie. The satellites orbiting far above the Earth, the ones that make modern navigation possible, must constantly correct their onboard clocks, accounting for the fact that time moves slightly faster for them, farther from Earth's gravity, than it does for us, resting quietly here below, closer to the planet's gravitational pull. Without that correction, the drift would compound, quietly, invisibly, until the entire system built to tell us exactly where we stand upon the Earth would slowly, steadily, fall apart. Imagine, then, a place where gravity grows far stronger still, where the curvature of space-time becomes so extreme that time itself begins to slow almost to stillness. Near the event horizon of a black hole, this effect becomes profound. To someone watching from a safe distance, an object falling toward the horizon would appear to slow down more and more as it approached, its light stretching, reddening, dimming, seeming almost to freeze at the very edge, taking, from the outside perspective, an infinite amount of time to ever fully cross that boundary, forever suspended at the threshold, forever arriving but never quite arrived. And yet, to the object itself, to whatever fell across that edge, no such slowing would be felt at all. It would simply fall, smoothly and without hesitation, crossing the horizon in what would feel, to it, like an entirely ordinary passage of time, unaware that from every other vantage point in the universe, it appeared to linger forever at the edge of disappearing. Two true stories, unfolding from the same single event, each entirely accurate from where it is told, neither one false, both simply shaped by the strange and quiet fact that time itself is not a single, universal river flowing the same way for everyone, but something more like countless separate streams, each carrying its own observer forward at its own particular pace, sometimes rushing, sometimes slow, sometimes nearly still, all of them, together, forming the vast and gentle current of spacetime itself, a fabric none of us can see, and yet all of us are stitched into, moment by moment, without ever feeling the thread pull tight. And if you were to follow that falling traveler further, past the point where outside eyes lose them entirely, past the last flicker of light stretched thin across the dark, you would find yourself asking the question that has quietly unsettled physicists for the better part of a century. What, exactly, waits at the center of a black hole? Not metaphorically, not poetically. What is actually there, if anything can be said to be there at all? General relativity, that beautiful and exact geometry Einstein handed to us, gives an answer, but it is an answer that seems to argue with itself the moment you look closely. The equations predict a singularity, a point, or perhaps not even a point, where the curvature of space becomes infinite, where density climbs without limit, where the smooth geometry of the universe simply stops being smooth. It is the place where the mathematics, which has been so reliable, so obedient everywhere else, quietly raises its hand and admits it does not know what happens next. This is not a flaw in imagination. It is a flaw in completeness. Einstein's equations describe gravity as the curvature of space and time, magnificently, at every scale we have ever tested them, from the fall of an apple, to the orbit of Mercury, to the bending of starlight around the sun, to the gentle chirp of gravitational waves crossing 1 billion light-years to reach 2 mirrors in the Louisiana pines. But gravity is not the only force whispering at the smallest scales. Down there, in the space smaller than atoms, smaller than nuclei, smaller than anything we have direct evidence for, quantum mechanics governs instead, a different set of rules entirely, probabilistic, grainy, built from uncertainty rather than smooth continuous curves. And at the singularity, these two great pillars of physics, general relativity, ruling the very large, and quantum mechanics, ruling the very small, are forced to occupy the same infinitesimal point at the same time. Neither one yields. Neither one explains what the other insists must be true. It is, perhaps, the deepest unresolved seam in all of science. Not a mystery of missing data, but a mystery of two truths that do not yet know how to speak to each other. Most physicists suspect that the singularity, as the equations describe it, a literal infinity, is not a real physical thing so much as a signpost. A place where our current theories are simply the wrong tool for the terrain, the way a paper map, however finely drawn, cannot describe the curvature of the Earth without eventually being folded, torn, or replaced by something else entirely. Somewhere in that final plunge toward the center, a theory of quantum gravity, one we do not yet possess in finished form, would presumably take over, smoothing the infinity into something stranger, but finite. Loop quantum gravity imagines space itself as grainy, woven from tiny discrete threads, which might refuse to compress past a certain minimum size. String theory imagines the singularity replaced by impossibly small, vibrating filaments of energy, for which infinite density may simply not be an option. Neither picture has been confirmed. Both remain, for now, only careful guesses, offered by brilliant minds standing at the very edge of what mathematics allows them to see. And so we are left with an honest kind of not knowing. Not the lazy not knowing of a question never asked, but the humbling not knowing that comes only after asking as precisely, as rigorously, as a species can, and discovering that the universe, at its most extreme, may simply outpace the language we have built to describe it. Consider, for a moment, what this means. Every black hole scattered across the night sky, and there may be as many as 100 million of them in our galaxy alone, most invisible, most silent, betrayed only by the way they bend the light of stars that pass too near, every single one of them carries, at its heart, this same unanswered question. A hidden interior. A place where the rules run out. We orbit these mysteries constantly, unknowingly, the light from distant galaxies bending gently around masses we will never see directly, tracing the outline of secrets we cannot yet open. But there is one detail more troubling still, one thread physicists have been pulling at since the 1970s, when a young researcher named Stephen Hawking proved something that seemed, at first, almost impossible. That black holes, despite their name, despite their reputation as the universe's most perfect vault, are not entirely black after all. That they leak. Slowly, faintly, across timescales longer than the current age of the universe by staggering margins, they radiate. And that faint radiation, drifting outward into the dark, carries with it a question that would eventually divide the physics community for decades. A question about memory, about permanence, about whether anything that ever fell into a black hole is truly lost, or whether, somewhere in the universe's deep and patient bookkeeping, it is somehow, impossibly, still preserved. This is what came to be called the information paradox, and it is worth sitting with slowly, the way you might sit with a single snowflake melting on your palm, watching it change shape without quite vanishing from existence. In quantum mechanics, there is a principle so foundational that physicists rarely think to question it, the way you rarely question that a mirror shows you facing the right direction. The principle is this: information is never truly destroyed. Not information in the everyday sense of facts or sentences, but something deeper, the complete quantum description of a thing, the precise arrangement of particles and their properties, which in principle could always be used to reconstruct the past. Burn a book to ash, and although you could never practically gather every scattered atom of smoke and soot again, the information describing that book has not vanished from the universe. It has only been scrambled, hidden, smeared out into a form so complex that unscrambling it is beyond any technology we could imagine. But it is, in theory, still there. Recoverable. Real. Now take that same book, and instead of burning it, drop it into a black hole. For decades, the assumption was simple, almost obvious. The book falls in, joins the mass of the black hole, and whatever fate awaits it, the information describing it is preserved somewhere within, sealed behind the horizon like a letter sealed in a vault. Complicated to retrieve, perhaps forever, but not destroyed. Just elsewhere. Except Hawking's discovery complicated that picture in a way that unsettled nearly everyone who understood its implications. If black holes radiate, if they slowly evaporate, losing mass over unimaginable stretches of time, shrinking, seemingly at random, particle by particle, until eventually, trillions upon trillions of years from now, they vanish entirely, then where does the information go? The radiation Hawking calculated appeared, in his original mathematics, to be purely random. Thermal. Featureless. Carrying no imprint, no fingerprint, no trace of what had fallen in to create it. Which meant that when the black hole finished evaporating, finished radiating itself away into that faint whisper of particles drifting into the emptiness, the information about the book, and everything else that had ever fallen in alongside it, would simply be gone. Not hidden. Not scrambled. Erased, in a way the rest of physics insisted should be impossible. Picture it slowly, because it deserves to be pictured slowly. A black hole is not eternal. It is, in the truest sense, evaporating even now, this very moment, releasing an impossibly faint mist of particles into space, a process so slow that for a black hole the mass of our Sun, it would take a span of time longer, by many, many orders of magnitude, than the current 15 billion or so years the universe has existed. And at the very end of that unfathomably long process, when the black hole has shrunk to nothing and dispersed entirely into radiation, the question is not whether the black hole disappears. It does. The question is whether everything the black hole ever swallowed disappears along with it, in violation of the universe's deepest and most trusted law of conservation. Or whether, somehow encoded invisibly in the subtle correlations of that radiation, in patterns too fine for Hawking's early calculations to detect, the information survives, smuggled out atom by atom, particle by particle, across the entire lifetime of the black hole, like a message passed slowly through a crowd until it reaches the far side intact. For nearly 50 years, this question sat at the center of theoretical physics, resisting resolution, forcing brilliant minds to reconsider assumptions they had once thought unshakable. And in recent years, the story has begun, cautiously, to shift. Using tools from an unexpected corner of physics, the mathematics of quantum entanglement, the strange invisible threads that link particles across any distance, researchers have found hints, calculations, entire new frameworks suggesting that the information may indeed be preserved after all. That the radiation, once thought perfectly random, may in fact carry within it an extraordinarily subtle imprint of everything that ever fell inward. Not the book itself, not its shape or its weight or the ink upon its pages, but the deep quantum information describing it, rewritten into a form so foreign, so distributed, that recovering it would require calculations of staggering complexity, and yet, crucially, not requiring anything to have been truly, fundamentally lost. If this is correct, and the growing consensus among physicists suggests it likely is, then black holes are not the perfect erasers of the universe they once seemed to be. They are something stranger. Processors, perhaps. Cosmic engines that take the information of everything they consume, every star, every fragment of light, every wandering mote of dust that ever crossed their horizon, and slowly, over spans of time longer than galaxies live, translate it into another language entirely. Encoding it, transforming it, never quite letting it go. And if that is true, then somewhere, hidden in the faint radiation drifting outward from every black hole in the sky, in a code we have not yet learned to read, is written the complete and total history of everything that ever fell into it, waiting patiently for a reader who does not yet exist, in a language no living mind has yet learned to speak. It is a strange kind of comfort, if you allow yourself to feel it that way, the thought that nothing is ever truly erased, only transformed past the point of easy recognition. That the universe, even in its most violent and crushing places, seems to lean toward preservation rather than loss. It is the same principle, in a way, that governs a wave crossing the ocean, changing shape entirely, gathering and releasing, and yet never once ceasing to be water. Perhaps that is the wrong comparison. Perhaps there is no comparison quite equal to it. But lying here, in the dark, breathing slowly, it is worth letting that thought settle for a moment. Nothing lost. Only changed. And yet, for all that black holes have taught us, about gravity, about time, about the strange partnership between information and existence, they still account for only a small fraction of what actually fills the universe. A smaller fraction, in fact, than most people ever realize. Because hiding behind the stars, behind the galaxies, behind every point of light the eye or the telescope can gather, is a far larger and far quieter mystery. One with no visible edges. One that has never been seen directly, not once, by any instrument humanity has ever built. We call it dark matter, though the name itself is something of a confession. Not a description, but an admission of not knowing. It is not dark the way a shadow is dark, an absence of light in a place where light could otherwise be. It is dark the way a locked room is dark to someone standing outside it, unable to look in, only able to notice again and again that something inside is clearly, unmistakably there. The story begins gently enough, in the 1930s, with a Swiss astronomer named Fritz Zwicky, studying the way galaxies moved within a distant cluster. By all visible accounting, by every star he could count, every glow of light he could measure, the galaxies did not have nearly enough mass to hold themselves together. They should have been flying apart, scattering into the void the way a poorly tied bundle of branches falls open the moment the string is cut. And yet they weren't. Something invisible, some unseen scaffolding of mass, was holding the whole structure together, exerting a gravitational pull far beyond what the visible matter could explain. For decades, this observation sat quietly at the edges of astronomy, noted but not yet understood, until the 1970s, when an American astronomer named Vera Rubin turned her attention to something closer to home, the rotation of galaxies not so different from our own. She expected, reasonably, that stars near the outer edges of a galaxy's spiral arms would move more slowly than stars closer to the bright, dense center, the same way outer planets in our solar system drift more slowly around the Sun than Mercury does, obedient to the pull of gravity weakening with distance. But that is not what she found. Instead, the stars at the edges moved just as quickly as the stars near the center, as though the galaxy were far more massive, far more extensive, than its visible light suggested. As though something unseen were wrapped around the entire structure, an invisible halo, extending far beyond where the light quietly gave out. This pattern has since been confirmed again and again, galaxy after galaxy, cluster after cluster, using tools far more precise than anything available to Zwicky or Rubin. Gravitational lensing, the way massive objects bend the light of galaxies behind them, curving spacetime just as Einstein's equations describe, has allowed astronomers to map the presence of unseen mass with startling accuracy, tracing its outline the way you might trace the shape of a hidden object beneath a draped cloth, guided only by the way the fabric bends and folds around it. And what these maps reveal, consistently, patiently, is that the visible universe, the stars, the planets, the gas, the dust, every glowing and luminous thing we have ever photographed or measured, makes up only a small fraction of the total mass out there. Somewhere near 5%. The rest, roughly a quarter of everything, is something else. Something that does not shine, does not absorb light, does not interact, as far as we can tell, with anything except gravity itself. It moves through our galaxy this very moment, indifferent, invisible, passing through stars and planets and the quiet spaces between atoms without so much as a whisper of resistance. It may be passing through you right now, as you lie here in the dark, a silent and patient presence, older than the light of any star you have ever seen, threading its way through the room, through your body, through the very fabric of this moment, leaving behind no trace at all except the slow gravitational pull that holds entire galaxies together, gently, across distances so vast that light itself takes millions of years just to cross from one edge of a galaxy to the other. We do not know, even now, what this substance actually is. Not with certainty. Not with the kind of confidence that lets a physicist write an equation and call the matter settled. What we have, instead, are candidates, careful, mathematically elegant guesses, each one chasing the same elusive presence from a slightly different angle. For a long while, the leading suspicions centered on something physicists named, almost playfully, WIMPs, weakly interacting massive particles. Particles that would carry mass, and therefore gravity, and therefore the pull we observe bending galaxies into shape, while almost entirely ignoring the other forces of nature. Rarely touching light. Rarely touching ordinary matter at all. Slipping through the universe the way a held breath slips through a house at night, present, consequential, and yet almost impossible to catch directly. For years, deep beneath mountains and old mine shafts, in laboratories shielded from cosmic rays by thousands of feet of solid rock, scientists have waited for exactly that, a single, faint collision between a passing WIMP and the nucleus of an ordinary atom. Tanks of liquid xenon, cooled and stilled to an almost perfect silence, sit in the dark, patient as monks, listening for the smallest possible flicker of an interaction. So far, the tanks remain quiet. Not disproving the idea, but not confirming it either, and with each passing year of silence, the space of possibility narrows, and physicists lean, cautiously, toward other candidates. One of these is smaller, stranger, almost humble in its scale, a particle theorized called the axion, so faint, so nearly massless, that if it exists at all, it might pass through entire planets without ever once disturbing a single atom in its path. Others propose no new particle at all, but rather a subtle correction to gravity itself, a suggestion that perhaps Einstein's equations, so extraordinarily successful everywhere else, simply behave differently at the vast, gentle scale of galaxies, and that no invisible mass is needed if gravity itself has been slightly misunderstood at those distances. This idea, though pursued seriously, has struggled to explain everything the WIMP and axiom models explain more naturally, and so, for now, most of the scientific community continues to favor the existence of some genuine, undiscovered form of matter, waiting quietly to be found. It is worth pausing here, in the stillness of not knowing, to notice something remarkable, that roughly a quarter of the entire universe is made of something we cannot yet name. Not a distant question, not an abstraction confined to journals and lecture halls, but a physical presence, woven directly into the architecture of every galaxy, including the one we call home. The Milky Way itself is thought to sit inside a vast, spherical halo of this unseen material, far larger than the visible disk of stars we associate with its shape, extending outward into the dark like the hidden roots of a tree reaching far beyond the shadow of its branches. We orbit within it. We are held together, in some quiet sense, by something we have never seen, and may never see directly, no matter how sensitive our instruments become. And yet, strange as this is, dark matter is not even the largest piece of the puzzle. It is, in fact, only the second largest. Because beyond the matter, seen and unseen alike, beyond every star and planet and invisible halo of unknown particles, lies something even more vast, even more mysterious, something that does not simply exist within the universe, but appears to be reshaping the universe's very destiny. In the late 1990s, two separate teams of astronomers, working independently, studying the light of distant exploding stars called Type Ia supernovae, stars whose brightness, remarkably, can be calculated with enough precision to serve as reliable cosmic distance markers, a kind of standard candle scattered generously throughout the universe, arrived at a finding so unexpected that both teams, at first, suspected their own instruments of error. They had set out expecting to measure the rate at which the universe's expansion was gradually slowing down, a deceleration caused by the mutual gravitational pull of everything within it, the way a ball thrown upward slows gradually under Earth's gravity before eventually falling back. This was the expected story, the one nearly every physicist had assumed correct for the better part of a century. Instead, they found the opposite. The universe was not slowing in its expansion. It was speeding up. Galaxies were not merely drifting apart, they were drifting apart faster with each passing moment, as though some invisible hand had reached into the fabric of space itself and begun, ever so gently, pressing the accelerator further down, pushing everything apart with a force that grew stronger, not weaker, the further into the future you looked. They called it dark energy, though the name explained nothing. It was a label for an absence, a placeholder for a force whose nature remained, and still remains, entirely unknown. Two teams of astronomers, working independently, studying the light of distant supernovae, had arrived at the same impossible number. Both had expected to measure a universe gently breaking. Both found a universe with its foot pressed to the floor. And when the results were checked, and checked again, and checked by rival groups hoping to find the error, no error appeared. The universe was, without argument, expanding faster now than it had 1 billion years ago. Something was pushing. Consider what this meant, quietly, for a moment, before moving further. Every galaxy you might imagine, every point of light scattered across the dark, was not simply coasting outward from some ancient explosion, slowing under the patient pull of gravity like a stone thrown across still water. It was being carried by a current that never stopped strengthening. The space between things was not empty in any simple sense. It was doing something. It held, within every cubic meter of nothing at all, a pressure that pushed outward, a whisper of energy inseparable from the vacuum itself. Physicists reached back, almost sheepishly, to an idea Einstein himself had introduced decades earlier and then abandoned, calling it his greatest blunder. He had added a term to his equations of general relativity, a constant, a small addition meant to hold the universe still, to keep it from collapsing under its own gravity in a model he believed, at the time, should be static, eternal, unchanging. When Hubble showed the universe was expanding, Einstein removed the term, embarrassed by what seemed an unnecessary complication. But now, 70 years later, that same mathematical thread reappeared, and this time it fit. The cosmological constant, once discarded, returned not to hold the universe still, but to explain why it would never stop accelerating outward, why the emptiness itself carried a hidden, restless energy. Today, when cosmologists divide the universe into its constituent parts, the numbers themselves feel like a kind of vertigo. Ordinary matter, the atoms that form stars and oceans, and every hand that has ever reached for another hand, makes up only about 5% of everything that exists. Dark matter, that invisible scaffolding of gravity without light, accounts for roughly 27% more. And the remainder, nearly 70% of the entire universe, is this dark energy, this pressure without a source, this force we can measure precisely and understand hardly at all. We live, each of us, inside a cosmos that is mostly a mystery pretending to be empty space. There is a strange humility in this. For most of human history, people believed the heavens to be the realm of certainty, of fixed stars and perfect order, while the earth below was the place of change and confusion. Now the situation has quietly reversed. We can weigh mountains and map the folding of proteins, but the majority of the universe, the fabric it is made from, remains a puzzle no laboratory can fully unlock. Dark energy does not clump. It does not gather around galaxies the way dark matter does. It is uniform, present everywhere in equal measure, a background hush filling every corner of existence, growing in total effect not because it strengthens locally, but because as space itself expands, there is simply more space, and therefore more of this pushing pressure, filling the growing distance between everything. This has consequences that stretch far beyond curiosity, into the very question of how the story ends. If the acceleration continues, and current observations suggest it will, then the far future holds a strange kind of silence. Trillions of years from now, an observer in our galaxy, or whatever remains of it, will look outward and see nothing. Not because there is nothing to see, but because every other galaxy will have been carried beyond the cosmic horizon, moving away faster than light itself could ever cross the widening gulf to reach them. Light from other galaxies will simply stop arriving. The night sky, over unimaginable spans of time, will empty itself of everything but the stars in our own galactic neighborhood, isolated islands adrift in a silence with no shore. It is called the Big Freeze, or sometimes heat death, an ending not of fire but of stillness, where stars burn down to embers, embers fade to black dwarfs, and even black holes, patient beyond comprehension, slowly evaporate into nothing through a process theorized by Stephen Hawking, a whisper of radiation escaping across unfathomable eons until even they are gone. What remains, if remains is even the word, is a universe of maximum entropy, a smooth and lightless expanse where no further change is possible, where time continues but nothing happens within it anymore, an ocean without waves, stretching on, and on, and on, past any horizon of thought, into a darkness that does not end because there is nothing left in it capable of ending. The timescales involved defy the ordinary meaning of the word long. A human lifetime, measured against the age of the universe so far, is already a flicker too brief to register, a single breath in a story that has been unfolding for nearly 14 billion years. But the future ahead of us dwarfs even that vastness into insignificance. The last red dwarf stars, the smallest and most miserly of all stars, burning their fuel with such patience that a single one might shine for 10 trillion years, will not begin to fade until long after every star we can see tonight has gone dark. And even then, the story continues. Stellar remnants, the dense cooling embers of dead suns, will drift through a universe grown black and cold, occasionally colliding, occasionally merging, in a slow demolition that stretches across numbers so large they cease to feel like numbers at all and start to feel like a kind of silence written in mathematics. Black holes, too, will have their turn to fade. Hawking's calculations suggest that even the largest among them, the supermassive giants anchoring the hearts of galaxies, will eventually radiate away every last trace of themselves, a process so slow that a black hole with the mass of a galaxy might take something on the order of 10 to the 100th power years to fully evaporate. Try, for a moment, to hold that number gently in your mind rather than grasp at it. It is not a number meant to be understood the way we understand a calendar or a clock. It is a number meant only to gesture toward a scale of time so far beyond human experience that the mind can do little but bow to it, the way one might bow before an ocean at night, not comprehending its depth, only sensing that it is there. And yet, strange as it may sound, even a universe that has gone dark and cold and empty is not quite the same as a universe that has gone still. Physics tells us that even in the depths of what looks like absolute nothing, in the quantum vacuum itself, something continues to happen. Particles and their antiparticles flicker briefly into existence and vanish again, borrowed for an instant from the uncertainty that governs all things at the smallest scales, a debt paid back so quickly that it barely counts as existence at all. This is not empty space in the way silence is empty. It is a kind of restless nothing, trembling faintly, forever. Some physicists, following this thought to its most unsettling conclusion, have wondered whether, given truly unimaginable spans of time, spans so far beyond even the evaporation of black holes that our 100-digit numbers begin to look small again, these quantum flickers might occasionally produce something more than a fleeting particle pair. Might they, on the rarest of occasions, produce a fluctuation large enough, complex enough, to briefly resemble a thought, a memory, a mind, assembled for a moment out of the trembling vacuum, aware of itself just long enough to wonder where it is, before dissolving back into the emptiness from which it came. These hypothetical entities have a name, half playful and half haunting, borrowed from the physicist who first raised the unsettling statistical question. They are called Boltzmann brains, and though most cosmologists regard them as a paradox to be resolved rather than a genuine prediction, their very possibility says something quietly vertiginous about the deep future, about how thin the line may be between absolute emptiness and the sudden, meaningless flicker of experience. It is worth pausing here, in the dark and the quiet, to notice how strange a turn this has become. We began by trying to measure whether the universe's expansion was slowing down. We found instead that it was speeding up. And in following that discovery all the way to its logical end, across trillions upon trillions of years, we have arrived at a place where the very distinction between something and nothing begins to blur, where a universe stretched thin and cold might still, in some faint statistical sense, dream. But there is another question hiding beneath all of this, one that has troubled physicists for longer than dark energy has existed as an idea at all. It has to do not with what the universe is made of, but with why time seems to move in only one direction. Why the past feels fixed and the future feels open. Why a shattered glass never gathers itself back up from the floor, though the equations governing its individual atoms would allow it, in principle, to do exactly that. It is called the arrow of time, and it is, in its own quiet way, just as strange as anything we have wandered through so far, tied not to galaxies or black holes, but to something called entropy, a concept that begins, of all places, with steam engines, and ends somewhere far stranger, in the very structure of the universe at its birth. In a moment so early, so compressed, that the word beginning barely applies to it in any way we would normally use that word. To understand why time moves forward, we have to go back to the 19th century, to engineers studying steam, trying to understand why heat always flows from hot things to cold things, and never, on its own, the other way around. A cup of tea left on a table will cool until it matches the room. It will not, given enough patience, spontaneously grow hotter by drawing warmth back out of the air around it. This simple, almost boring observation, when examined closely enough, turned out to contain one of the deepest truths in all of physics. The concept that emerged from this was entropy, a measure not of energy itself, but of disorder, of the number of ways a system's particles can be arranged while still looking, from the outside, the same. A tidy room has very few configurations that would still count as tidy. A messy room has an almost uncountable number of configurations that would still count as messy. This is why rooms drift toward mess and not the other way around, not because of any mysterious force pulling them there, but simply because messy states vastly outnumber tidy ones, and left alone, a system tends to wander into whatever state is statistically most likely. Entropy, in this sense, is not a force. It is a tendency, an inevitability born from probability itself, from the simple fact that there are so many more ways to be disordered than to be ordered. The second law of thermodynamics states this tendency as something close to an iron rule of nature, one of the very few laws in physics that seems to point in a direction. In an isolated system, entropy will, on average, always increase, never decrease. Ice melts. Perfume disperses through a room and does not gather itself back into the bottle. Stars burn their fuel and scatter it as heat and light across the emptiness of space, never drawing it back in. Every one of these small, ordinary events, the kind that happen constantly, unnoticed, all around us, is a tiny thread in the same vast tapestry, all of them pointing the same way, all of them part of what physicists call the arrow of time. But here is the puzzle hiding inside this ordinary observation, the puzzle that has troubled physicists for well over a century. At the smallest scales, the fundamental laws of physics do not care about direction. The equations describing how two particles collide look exactly the same whether you run them forward or backward through time. A film of two atoms bouncing off each other would look equally plausible played in reverse. There is nothing in the underlying mathematics of motion that says the future must be different from the past. And yet, when you gather enough particles together, when you build a universe out of them, direction suddenly, mysteriously, emerges. Somewhere between the timeless symmetry of individual particles and the felt, undeniable one-way flow of a human life, an arrow appears. And no one has ever fully explained where, precisely, it comes from. The most widely accepted answer reaches all the way back to the beginning of everything, to the earliest moments after the Big Bang. For entropy to have been increasing ever since, for the universe to have been moving steadily from order toward disorder for nearly 14 billion years, it must have started in a state of extraordinarily, almost incomprehensibly low entropy, a state of near-perfect order, more ordered than nearly any configuration physics can easily explain. Some physicists have calculated just how improbable such a starting condition would be if chosen at random from all the ways a universe could conceivably begin, and the number that emerges is so vanishingly small, so many countless zeros deep, that words like unlikely feel almost too gentle to hold it. This is sometimes called the past hypothesis, a quiet assumption sitting beneath nearly all of modern cosmology, an admission that we do not truly know why the universe began in such a special, ordered state, only that it must have, for everything that followed to make sense. It is strange to think that the reason a glass shatters and never reassembles, the reason memories move only forward and never in reverse, the reason you feel yourself aging one moment at a time rather than unaging, traces all the way back to a single, improbable condition at the very edge of time itself, an ancient asymmetry, inherited silently by every falling leaf, every dying star, every breath drawn and released, ever since. And if that is true, then time's arrow is not truly a law of nature in the deepest sense, not something written permanently into the fabric of the universe the way gravity is. It is closer to an inheritance, a kind of momentum carried forward from an extraordinarily rare beginning, still unwinding, still playing out, in every corner of existence, including this one, including the quiet dark around you now, where entropy continues its slow, patient work, and somewhere beyond the reach of any clock, the universe keeps moving, gently, irreversibly, forward. toward a horizon none of us will live to see, and yet one that shapes, quietly, the character of every moment we do experience. There is something worth sitting with here, in the dark, before moving further. The fact that you can remember yesterday but not tomorrow, that you can shape the future but only observe the past, is not some obvious feature of reality that requires no explanation. It is one of the strangest things about existence, so woven into the texture of every waking moment that it becomes invisible, the way a fish might never notice water. And yet physics suggests that this most intimate of experiences, the felt difference between what has happened and what has not yet happened, traces back to a condition present in the universe before there were stars, before there were atoms heavier than hydrogen and helium, before there was anything resembling a mind capable of noticing the difference at all. It is a peculiar kind of inheritance when you think about it slowly enough. The low-entropy beginning of the universe did not know, could not have known, that it would eventually give rise to structures capable of reflecting on their own passage through time. And yet here we are, each of us a temporary, elaborate arrangement of matter, unusually low in entropy compared to our surroundings, holding ourselves together for a few brief decades against the universal tendency toward dispersal, before entropy claims us as it claims everything else. Life itself, in this view, is not an exception to the second law of thermodynamics. It is one of its more extraordinary expressions, a local, temporary pocket of order, purchased at the cost of increasing disorder elsewhere, in the heat radiated by every cell, in the entropy released by every star that made the elements our bodies are built from. This reframes something. It suggests that a sunset, a heartbeat, a memory forming in the quiet architecture of a sleeping mind, are not separate from the vast cosmic story unfolding above and around us. They are continuous with it. The same tendency that scatters starlight across the emptiness of space, that will one day dim the last ember of the last star, is the tendency animating the small, ordinary miracle of a single evening drawing to a close. We are not observers standing outside the arrow of time, watching it pass. We are, each of us, part of its passage, small local increases in the disorder of the universe, briefly, remarkably, organized enough to wonder about the very process carrying us forward. Some physicists have pushed this line of thought even further, into stranger territory still, wondering whether the arrow of time might not be a single, universal current at all, but something closer to a strong regional trend, a slope down which our particular corner of existence happens to be sliding. In theory, if entropy is simply a matter of probability, and if the universe is vast enough or eternal enough, there could exist other regions, other pockets, where the gradient runs differently, where an unlikely, low-entropy fluctuation might birth a small bubble of order that, from the inside, would experience its own arrow of time, its own forward march toward disorder, entirely disconnected from the current flowing through the region we happen to occupy. It is a deeply speculative idea, sitting closer to philosophy than confirmed science, but it emerges from taking the mathematics of entropy seriously enough to ask what it would truly mean for something so fundamental to be, at bottom, a matter of statistics rather than a fixed and universal law. What remains solid, what observation after observation continues to confirm, is simply this: the universe had a beginning of remarkable order, and has been unwinding, ever so slowly, toward disorder ever since, and this unwinding is what we experience, in our small human way, as the passage of time itself. Every clock that has ever ticked, every star that has ever burned, every wave that has ever broken against a shore, has been keeping time with this same vast, quiet process, a process that began before there was any observer present to notice it, and one that will continue long after the last observer is gone. And so we return, gently, to where this long unfolding began, to a universe that started impossibly small, impossibly hot, impossibly ordered, and has been expanding, cooling, and dispersing ever since, first slowly by our reckoning, then, as we discovered through the light of dying stars 100 years later, faster and faster, carried by a pressure hidden in the vacuum of space itself, toward a future so distant, so cold, and so strange that the mind can only approach it the way one approaches sleep, not by understanding it fully, but by letting go, slowly, of the need to hold on any longer, drifting instead toward whatever comes next, unresisting, weightless, carried forward by the same quiet current that has carried everything, always, from the very beginning. And if there is a lesson folded quietly inside all of this, inside the deceleration that turned out to be acceleration, inside the entropy inherited from a beginning too strange to fully picture, it may be simply this: that the universe is not required to make itself comprehensible to the creatures who happen to arise within it. It does not owe us a story shaped for our comfort, or an ending shaped for our understanding. And yet, somehow, against every reasonable expectation, it produced beings capable of measuring the light of exploding stars 90 million years after those stars died, capable of noticing that the light was fainter than it should be, capable of following that faint discrepancy all the way down into the deep architecture of space and time itself. This, too, is a kind of wonder, quieter than the acceleration of galaxies, but no less strange. That matter, arranged just so, for a brief moment, in a small and unremarkable corner of one ordinary galaxy, could turn and look back at the universe that made it, and ask what it was made of, and receive, patiently, an answer. We have wandered, across this long night, through a great deal of darkness. The darkness of matter that cannot be seen, only felt through its gravity, holding galaxies together like an unseen hand cupped gently around a flame. The darkness of energy filling every corner of empty space, pushing everything apart with a patience that only strengthens with time. The darkness of black holes, where light itself cannot escape, and the deeper darkness of the vacuum, trembling faintly with particles that flicker into being and vanish again before they can be named. And beneath all of it, the darkness of not knowing, the humbling, honest darkness of a universe that remains, even after a century of extraordinary discovery, mostly a mystery to the minds trying so carefully to understand it. But darkness, in this context, was never the opposite of understanding. It was simply the shape understanding takes when it is still unfinished, when the map is still being drawn, when the light from distant places is still, even now, crossing the vast gulf of space to reach a telescope not yet built, a mind not yet born, a question not yet asked. Every discovery threaded through this long narration, the expansion, the acceleration, the invisible scaffolding of dark matter, the low-entropy dawn of everything, was once itself a kind of darkness, an absence, a gap in what was known, before someone, somewhere, patient enough and curious enough, turned their attention toward it and waited for it to answer. Perhaps that is the quiet thread holding this entire story together, from its faintest beginning to this final, drifting moment. Not the galaxies themselves, vast as they are, nor the forces pulling them apart, nor even the strange arithmetic of entropy governing the shape of time. But the simple, recurring fact that somewhere within this cooling, expanding, endlessly diluting universe, there arose, however briefly, however locally, something capable of looking upward and outward and wondering. A universe assembling, out of hydrogen and starlight and 13 billion years of unlikely history, an audience for itself. However the story ends, whether in the slow silence of the Big Freeze, or in some deeper mystery still waiting to be uncovered in the folded mathematics of dark energy, this fact will remain true of the part we were given to witness. For a while, in the vast and mostly empty dark, something noticed. Something wondered. Something, for the smallest sliver of cosmic time, was awake. And so, as this long telling draws to its close, there is nothing more to solve tonight, nothing more to calculate, no further figure to carry forward into wakefulness. The galaxies will keep receding, whether watched or unwatched. The stars will keep burning down to embers on their own unhurried schedule. The entropy of the universe will keep its slow, patient increase, indifferent to whether you are awake to measure it or asleep, dreaming, somewhere far beneath its quiet, continuous unfolding. There is nothing left to do now but let go of the thread we have been following, and let it drift gently out of reach, the way a hand slowly loosens around something no longer needed. The universe does not require your attention to continue. It only ever asked, gently, for a little of it now and then, in between the long stretches of ordinary life, and you have given that tonight. That is enough. Let the vast dark do what it has always done, indifferent and enormous and strangely beautiful, while you, small and warm and temporary, drift downward now into your own quiet entropy, your own gentle dispersal into rest, carried, as everything is carried, softly and without resistance, towards sleep.